Great. Okay, so welcome to lecture 14. I am David Sontag. I am one of the faculty instructors for this course. And for this last lecture of the semester, I'll be the one who will be presenting. And it'll be a lecture about machine learning in healthcare. As in previous lectures, you may ask questions either via the chat or via discourse. We highly recommend discourse because I myself won't be able to monitor the chat other than at a couple of choice moments when I ask you specific questions, and I will be monitoring the chat at those instances to see what your responses are. Otherwise, please ask in discourse, and one of the course staff will unmute themselves and ask me those questions. Before I kick off the actual material for today's lecture, I want to just remind us a couple of announcements. First, the subject evaluations are now open, and we have posted a link to the evaluations on the course website. Please complete them by December 14th, and this course will be offered again in a virtual format next semester. And given that this is still very new format for us, your feedback is going to be extremely valuable for the next semester's course staff. Secondly, we'd like to emphasize that all course extensions must be completed by Wednesday the 9th. That's less than 1 week from the normal due date, but that's important because MIT rules do not allow us to have anything later than the last day of class be due. So I'm a computer scientist, and over the last 10 years, I have pivoted my research from pure machine learning research to machine learning research, which looks at questions motivated by healthcare. And the reason why it's so exciting to be a computer scientist working in the health space now is that there's a wealth of digital health data available. That data ranges from unstructured clinical notes to imaging data, laboratory tests, vital signs. More recently includes data like proteomics and genomics, and even things that we don't traditionally think about as health data, but which give us a lens on a patient's health, data like mobile activity information or data from a Fitbit type device. And the fact that this data is now in digital form means that it gives us an opportunity to use machine learning algorithms both to learn from the retrospective data and to deploy interventions such as clinical decision support on top of that digital data at the point of care. Health data lives in a variety of different settings, and it's really important as we think about how we're going to tackle a few different scenarios that we'll discuss in this lecture today, where that data might come from. For example, one major source of health data is in providers or hospital systems. So for example, many of you students go to MIT Medical. MIT Medical has an electronic medical record. And across the United States, the adoption of electronic medical records has increased dramatically since 2008, from 9.4% to well over 85% today. That data consists of some of the aspects that I mentioned earlier, such as clinical notes and imaging data. Another major source of health data consists of data that's being collected by health insurance companies. And you can see in this diagram here where I show you the three major players in healthcare infrastructure, providers, payers, and patients, that their relationships between them, data passes back and forth. So for example, your doctor, when they want to get paid for a service performed for a patient, they send a bill to the health insurance company. So for example, if you're a MIT student, your health insurance company is probably Blue Cross Blue Shield, if you're covered by the MIT plan. Otherwise, it might be by whatever your parents' plan is. Now, that bill actually has a lot of valuable information in it about what happened during that visit. So for example, here I'm showing a concrete instantiation of one such bill. And you see that hold on, I'm trying to see how I can get my mouse to show. I need to change the settings. One moment.
You can click on the pencil icon in the bottom left and then choose laser. It's the gray icon.
Thank you. Can folks see my mouse now?
Yes, we can see your mouse. If you use the laser pointer, it's a bright red dot and it will be a little better.
Yeah,
But the mouse is fine.
I can't find the laser pointer option, unfortunately. Oh, I see it now.
A laser up there, not that one. Yes.
Great, thank you very much. All right, so over here, this is an example of a bill that's sent from your doctor to your health insurance company to get paid for the services they provide. You see that there are what are called diagnosis codes that refer to the reasons for performing procedures. For example, here there's a code that denotes diabetes, another code that denotes a heart condition called coronary artery disease. In addition, there are several different lines corresponding to different procedures that were performed. Each procedure has a number associated to it. So this is standardized, and of course, a cost. And on the right-hand side here, you have an ID for the provider that performed that service. Now, this health data, the fact that there's been such a wealth of digital health data available has been taken note of by industry. And we see all of the major tech players now, places like Apple, Google, Amazon, all getting involved in the healthcare industry. So for example, Apple recently launched, as part of their Apple Watch, a machine learning based product which can read a patient's EKG. So it's measuring a patient's heart through a sensor on the watch and can diagnose a number of heart conditions. Google has launched a number of products that are based on computer vision. So for example, they have one which can help diagnose diabetic retinopathy, which is a condition caused by diabetes and which goes undiagnosed in many parts of the world due to not having sufficient number of doctors who can read those images. Amazon has released products on their cloud platform, which allows hospital systems to upload their clinical notes, and it'll perform a number of natural language processing on top of those clinical notes to help with, for example, that type of billing that I showed you earlier, which diagnosis codes to submit to health insurance companies. There are also a number of startups working in this area. So for example, a couple of my favorite startups are looking at how one can change pathology or medical imaging by developing devices that can be used by less trained physicians. So for example, nurses instead of trained technicians, to do, for example, imaging of the heart. And this is going to be very impactful for starting to move medical care away from hospital settings and closer to patients, and furthermore, also really starting to fill in the gap in many places in the world where there simply aren't enough trained technicians. And these startups are ranging from a number of different fields, such as those imaging fields that I mentioned, but also areas like mental health and improving communication between patients and providers, improving quality management, and so on. So in today's lecture, I'm going to be doing a number of brief case studies where we're going to dive into a few of these application areas of machine learning healthcare from the lens of the material that you learned from lectures 1 through 13. I'll start out with an example of supervised machine learning for risk stratification. Then, and that'll be the vast majority of the course, of the lecture. Then I'll talk about a use of unsupervised learning, in particular k-means clustering that you saw in last week's lecture. And I'll show how one can use that to discover subtypes from asthma, which you might recall was one of the optional questions in the lab last week. Finally, I'll give an example of reinforcement learning in healthcare and show how one can use that to better manage patients with septic shock in hospital environments. And I'll close with a couple of comments about what makes healthcare different from many other application areas of machine learning, and also some suggestions for future courses you could take to further learn about machine learning here at MIT. So let's start with the following scenario. As I imagine many of you have been tracking, we have been getting very close to having a vaccine approved in the United States for coronavirus. And over the next couple of months, there's going to be an enormous effort to get our population vaccinated. But in the first couple of months, there there won't be enough vaccines for everyone to be vaccinated. And so a number of ongoing efforts are trying to think through what population should one vaccinate. Questions about should one vaccinate first healthcare workers, frontline workers, elderly, and so on. And I'm not going to focus on the question here of who should get vaccinated, but I want us to be thinking about, once that decision has been made, what can we best do to achieve that goal? So in particular, let's think about an elderly population. Almost all of the current guidelines are going to prioritize individuals above the age of 65 very soon. In the next couple of months, they will be eligible for getting a vaccine. But not all of them will know or prioritize getting the vaccine themselves, despite the fact that they're eligible to get it. So we can imagine that the government might start a service where they are going to have a team of call workers that are going to be picking up the phone and calling elderly individuals who are most at risk of having complications due to COVID, and working with those individuals to try to get them to a local clinic where they could be vaccinated. You could also imagine having nurses sent to patients' homes to do vaccinations at home in some cases. But one of the major challenges, give me one moment. One of the major challenges in doing such outreach is that it's very costly, and one might only have funding in order to, for example, send nurses to a certain number of individuals' homes or facilities. And that leads to a really important question. How should one prioritize those resources? So for example, one way of trying to frame this where machine learning might be able to provide some light is that we could ask, who are the individuals who are most likely to have poor outcomes were they to be infected with COVID, with the coronavirus? Now, it's very difficult to try to think through the question of who's likely to have poor outcomes from a machine learning perspective, because we have poor data on the base denominator, who actually was infected. However, we do have very good data on who was hospitalized. And a slight reformulation of this question in order to try to tackle it with machine learning is to ask not about who has poor outcomes of those infected, but of those who are hospitalized, of which only a small fraction of them end up having poor outcomes, which of those end up having poor outcomes, such as admission to intensive care unit or death. And this one can start to try to tackle with data that we have, because there are very good records of who's been hospitalized and who has poor outcomes among those who have been hospitalized. So this question has been studied by a number of different authors already. And for example, recent work from New York City, from Korea, from California have looked at questions such as, of patients who've been hospitalized, what factors, whether it be past medical history or factors that patients present with when they're hospitalized, lead to those poor outcomes. And a number of different factors were surfaced. For example, older age, and that's one of the reasons why individuals over the age of 65 are being prioritized. Past conditions such as hypertension, which means high blood pressure, obesity, diabetes, and so on. So one approach that one might take is, we're going to use machine learning algorithm to try to predict these poor outcomes from electronic medical records, and then prioritize individuals based on those predictions. But the challenge with using that approach is that electronic medical records are very siloed. And so such a machine learning algorithm would have to be deployed de novo at every single institution, which is going to be very slow, expensive, and was unlikely to be possibly rolled out in a short period of time. And so this is where, in this hypothetical scenario, one of the most important machine learning questions comes to mind, which is, what data do you have available, and how can you make use of that data despite the fact that it might be very imperfect? And so what I'm going to do is I'm going to walk you through a hypothetical scenario where we think through what data to use, how we would process it, and how we would evaluate the result in order to try to tackle this problem. So I'm going to propose that what we should be using for this is data that's available at a national scale, in particular, health insurance claims. Remember, I told you that providers have to submit bills to their health insurance company in order to get paid. And I showed you an example of what those bills look like. Well, the biggest health insurer in the United States, in particular, the one which is most relevant to elderly individuals, is the Center for Medicare and Medicaid Services. And CMS has data on most individuals, most Americans over the age of 65. Whether you're poor, whether you're rich, almost all individuals in the United States are covered by Medicare once they reach a certain age. And thus, if one thinks about how one could very quickly both train and deploy a machine learning algorithm that could risk stratify at a national scale, that data is perhaps where we should be looking. So here's the hypothetical study design, which I want us to think through as part of this. Let's take all data from patients hospitalized with COVID-19 from March to July in the United States, data that's available from Center for Medicare and Medicaid Services. We're going to extract features from the data pre-hospitalization, and we're going to attempt to predict whether patients have poor outcomes during hospitalizations. In particular, we'll design a binary classification task where we have a label Y, which is 1 if the individual is admitted to the intensive care unit or expires, dies during the hospitalization, and 0 if they are discharged alive without having had to be admitted to an intensive care unit. And again, as an important disclaimer, I have not done the study that I'm proposing here. This is just a thought exercise for us, thinking about how we would try to tackle an important problem today using machine learning. So let's now start thinking about how one would try to derive features from this data set. Now, I just said that the labels are going to be derived from that hospitalization. And we're going to be focusing on just patients who have been hospitalized with COVID-19. Let's just say 19, not 10. Well, we could go back in time to pre-hospitalization and look at all of the type of data that would be available to the health insurance company. In particular, as I mentioned, every single visit with a health provider is going to have some records attached to it. So if the patient has gone to their primary care physician and they have high blood pressure noted in as a diagnosis code, we will have a record of that. If the patient goes to CVS pharmacy and fills a prescription for high blood pressure, we will have a record of that. If the patient has a telemedicine visit with their dermatologist, we will have a record of that. So the first question that I want us to be thinking about now is, how do we take this time series data and try to construct a feature vector from it? And notably, you can see here that some of the factors which have been discovered in earlier work in, for example, using electronic medical records do show up here. We mentioned how hypertension is a factor which seems to be predictive of poor outcomes. And we see that hypertension, which is high blood pressure, is recorded in previous patient visits. So that's something that we might be able to distill from the data. But if you dig deeper into the literature, you'll see that it's not just the patient having hypertension, which is predictive. In fact, it's having complicated or uncontrolled hypertension, meaning if the patient is not being well managed for their hypertension, if their blood pressure is high, despite the fact that they are on medications, or if they're not taking the right medications, those are the patients who tend to do poorly. And importantly, you have that information here. So you have records of whether patients are on medications. You have records of how often they're seeing physicians. And although we don't have direct measurements of whether the patient's hypertension is being controlled appropriately or not, one might be able to try to pull that out of this data via a algorithm that can detect very subtle signal in high dimensional data, such as a machine learning algorithm. So to dig a little bit more into the data, here's what it actually looks like. And what I'm showing you is a patient timeline, and I'm showing you with each bar here when a data element is observed in the data for this hypothetical patient. So I told you that we have medical claims. With those medical claims, we have these diagnosis codes. The diagnosis codes are encoded in a ontology known as ICD-10. This is a hierarchy where the top level hierarchy denotes, for example, neoplasms for cancers. There are another set of codes corresponding to diseases of the blood, another set of codes corresponding to endocrine disorders like diabetes, another set of codes corresponding to mental health issues. And if you dive deep into this hierarchy, you'll see that it is extremely detailed. We're getting really rich information about the past diagnoses of patients. For example, there's even a diagnosis code for bitten by a turtle or bitten by a sea lion, struck by a macaw. These are some of the more rare codes, but it gives you a sense of the richness of the data that could be encoded in these health insurance claims. We also know for every visit what specialist the patient doctor visited. Was it a primary care doctor? Was it a endocrinologist, a dermatologist? And we know where the visit was. Now, I talked about data being derived from pharmacy records, and these medications will have records of a code for the specific medication that's called the National Drug Code, or NDC code. If you take a medication off of your medication cabinet and you look at the box, you'll see that NDC code listed in the box. And so every medication has a unique identifier, which allows us to think about how to construct features from the presence of a medication in a patient's medical record. We know the number of days supply, and we know the provider who prescribed it and when. So a traditional approach to feature construction might take some of the factors that earlier work using electronic medical records had shown already to be predictive. You might take the patient's age, their gender. You might try to derive from all of the data I showed you whether the patient has hypertension. For example, looking at a set of hypertensive codes, looking at medications that are used to treat hypertension, and saying if any of this set of codes or any of this set of medications are present, then the patient has hypertension, yes or no, 1 or 0. You could do the same for other conditions like diabetes, cancer, and so on, and construct a feature vector of 20 or 30 or 40 different features, which are risk factors that were conjectured to be predictive of patients having poor outcomes when hospitalized with COVID-19. So this would be a traditional approach to feature construction. And one of the major challenges with these types of traditional approaches is first that they're very time consuming to create. So that notion of coming up with the list of things and then seeing how does one derive whether the patient actually has hypertension by what is the set of diagnosis codes to look at? What is the set of medications to look at? That takes a lot of time from a data scientist or from a domain expert. The second challenge with these more traditional approaches is that they miss a lot of the subtle detail around around the patient's condition. So I spoke about how it's not just whether the patient has hypertension or high blood pressure that's predictive, but whether it's not being managed appropriately. And that is something which is really, really hard to derive from the patient's data manually. There's simply no good characterization which is known that works well for large numbers of patients. So the approach that we're going to take in this hypothetical example is one which is more of a black box machine learning approach. And although this is a hypothetical example, this is one which I have used very similar approaches on exactly the same sort of data for a number of other non-COVID related conditions. And so I know that this type of approach works. So the analogy that we're going to be drawing is to something that we've seen throughout the course so far. When we've talked about, for example, text classification, we said, how would we take a text document, which has a number of words, and, for example, learn a classifier to label an email as spam or not spam? And we said that a very simple approach to try to do that might be to create one feature for every word in the vocabulary with an indicator of whether that feature is 1 or 0, which tells us did that word appear in the email or not? Now, for this type of data, I'm going to recommend a very similar approach to extracting features from the patient's longitudinal health records. We're going to look we're going to first create some features just from some basic demographics like the patient's age, gender, and so on. Then we're going to look at a number of other features that look at their health insurance coverage. And I'll come back to why that's relevant in just a couple of moments. Those two are sort of the more standard set, and everything else that I'll be referring to now are what I'll call as the bag of words features. So for example, we'll create one feature for the service place where patients are going. So have they been to a primary care doctor? Have they been to an urgent care clinic? Have they been to a hospital? Have they been to a regular doctor's office? And for each of these service place categories, we're going to just create a single binary indicator for has the patient been to that service place ever? 1 or 0. Now we'll do the same thing for these other categories. For example, of all of the medications, there might be we might look at the 1,000 most popular medications. We're going to create a single binary feature for was this medication ever filled? Yes or no. Where they're going to look at all possible procedures that could have been performed, or let's say the top 1,000 most common procedures. And we'll say, has this procedure ever been performed for the patient? Yes or no. And we'll do the same for the diagnosis codes. So we'll look at all of the different, let's say, top 10,000 ICD-10 diagnosis codes, and we'll look at, has this diagnosis code ever been recorded for a patient? Yes or no. Now, you might be wondering, whether the code has been recorded or not only tells you part of the story. For example, whether you filled this medication in the last 3 months might be very different from whether you filled the medication in the 3 years ago. And so the way that we're going to bring in the temporal information here in this hypothesized approach is by redoing this whole procedure I just mentioned now once for every time window. So we will create one set of features by performing that procedure I just showed using all of the patient's past medical history. We'll then repeat the process now restricted to just data from the past 24 months. And we'll repeat the process using data from just the past 6 months. That will then concatenate each of those feature vectors together, and we get the overall set of features that we'll use to predict the patient's outcomes. Overall, we might have tens or hundreds of thousands of features, and so we're going to need a machine learning approach that can deal with the fact that we're in a very high dimensional setting and can prevent us from overfitting. I'll just pause briefly to see if we have any questions.
None so far. Yeah.
And I saw a comment about disabling annotate on the screen. Has that been done?
I think that's for you. So if you go to view options on the top, you should just like where you're sharing the screen, just get rid of the annotate option.
Great. Okay, hopefully that's done.
I can still see the option to annotate your screen.
On the bottom or in the top? Because I don't see it.
On the top, it should say like you're sharing your screen, and then on the side it should say view options. And then if you click down, it should just disable the annotate, just like uncheck it.
Hide names of annotators. Did that work?
I don't think so.
I think you're okay without that option.
Yeah.
Okay, yeah. Okay, so the technique that we're going to propose to use here is one that you've already seen in a recent laboratory where we asked you about how you would tackle these different scenarios of machine learning. And one of the options that we had suggested in that lab was doing logistic regression with what was called L1 regularization. So I'll briefly walk you through what I mean by this, just to remind us. So as Tamara presented in the lecture on logistic regression could be formulated by the following objective function. We're going to sum over the little n data points. Our loss function is going to be negative log likelihood. We're going to use as our predictor, which will give us the probability of a individual having a poor outcome from COVID-19. We're going to use for that a linear model parameterized by a weight vector theta. That linear model is going to feed into a sigmoid, which will give us the probability of 1, which is going to be a number between 0 and 1. And we're going to evaluate the likelihood using that probability of the true label, whether the patient truly had a poor outcome when hospitalized with COVID-19 or not. And that label is given to you by YI for the ith patient. So that is the unregularized logistic regression objective function. And what we saw in class is that one way to try to prevent ourselves from overfitting would be to use L2 regularization, where we add onto the objective function a penalty for the squared norm of the weight factor theta. And just to remind you, by the squared norm, what we mean is we sum over the different dimensions of the weight factor of that weight, the dth weight squared. Instead of that L2 regularization, what we often do using this type of data is L1 regularization. And L1 regularization has the property that it tends to result in very sparse solutions. And the reason why that makes a lot of sense as a type of method for controlling for the number of high-dimensional features is because in this data set, by the way that we constructed the feature vector, most of the features are irrelevant or not useful. And that we expect that there are only going to be a small number of features that are actually predictive of this poor outcome. So by encouraging the learning algorithm to find a sparse weight vector, it's using some prior knowledge we have that the hypothesis space that we want to be searching within is one of sparse weight vectors. And as a result, we're going to be able to prevent ourselves from overfitting to the large weight vector, even if we have a very small number of labeled data points. So this L1 regularization, if we look on the right-hand side, is defined as summing over the features of the absolute value of the dth weight theta d. So you should be comparing this absolute value to the theta squared term shown in the bottom. We can then use one of a number of different optimization algorithms, for example, variants of stochastic gradient descent, in order to minimize this overall objective function. Now, intuitively, the reason why using this L1 norm results in a sparse weight vector is because when you're minimizing that objective function, you could think about the first term in the objective function over here, this L negative log likelihood, as some convex function. It's a convex function when we're using a linear model, as we are here. And we could think about what are the solutions that it could reach if we were restricting the weight vector to, for example, have any constant value according to theta square, according to the L2 norm, or any constant value according to the L1 norm. Intuitively, you could think about trading off. If you were to trade off this value being 10 or this value being 10, what solutions does that enable you to find in terms of the original objective function? So on the squared norms case, the picture you should be having in mind, if you had just two weights, theta 1 and theta 2, would be something like this. So if that squared norm were equal to 10, then the weights would have to be something along this circle. On the other hand, if the L1 norm were equal to 10, then the weights would have to be something along this diamond shape. So again, this first axis we'll call theta 1, the second axis theta 2. Now, if you look at the left-hand side, the solution that minimizes the objective function that lives along the circle is sort of this solution over here. Whereas on the right-hand side, the solution which minimizes this objective function according to that constraint is actually at this corner point. And that's one of the reasons why, or intuitively, why using this L1 regularization tends to result in sparse feature vectors, sparse weight vectors as a solution. Now, once one has learned the model, the next thing that we typically do is start looking at the model and trying to introspect, does it make sense? And the reason why this is so important is as a sanity check for whether we set up our problem appropriately. Often we will find by inspecting the weight vector errors in our machine learning formulation. For example, we might easily detect that that there was label leakage by recognizing that some weight, which really doesn't make sense, is much higher weighted. And this type of introspection by looking at what features have non-zero weight is much easier to do in the setting where you use a L1 regularization as opposed to L2 regularization, because there are many fewer features that have non-zero weight, and you can tend to just look at all of them. Now, the second thing which is important in thinking about how we would actually use the results for solving the original problem that we set out to solve, which recall was prioritizing outreach to patients who have who are eligible for having a vaccine. We want to figure out who we should be contacting in order to help them, for example, or get them to their local clinic. We need to understand, well, as a function of the number of people who we can actually outreach to, how many of them might actually actually have poor outcomes according to the predictions made by this algorithm. And to characterize that, we use what's known as the receiver operator characteristic curve. You'll see this often in the machine learning literature under the acronym ROC curve. Now, the ROC curve takes your predictive model. Remember, here we use logistic regression, so we get a probability out. And it's going to look at, if we were to threshold that probability at a variety of different values, what true positive and false positive rates are achievable by that threshold. Here I'm showing you just two hypothetical models. For example, a model which is trained using just those traditional risk factors that I showed you originally, and then the second model that I proposed, where I said we're just going to include this bag of words feature vector, which I'll call the full model. So the ROC curve will plot for every possible choice of threshold. We're going to look to see, okay, if we were to make those predictions according to that threshold. So let's say if we put a threshold at 0.5 and we said everyone with a probability higher than 0.5, we're going to predict to be 1. Everyone with a probability less than 0.5, we're going to predict to be 0. And we ask, well, of the ones we predicted, of the ones who were truly 1, what fraction of them, of the ones who were predicted to be 1, what fraction of them truly went on to have poor outcomes? That's what's known as the true positive rate. And if we look at, of the ones who were predicted to be 0, what fraction of them went on to not have poor outcomes? That's the false positive rate. And that gives you 1 point along this curve. And if you're to change that threshold from 0.5 to 0.6, you get another point along this curve. Now, one could try to summarize how good one algorithm versus another algorithm is by comparing these two different curves. And one statistic that can be useful for trying to compare one curve versus another is the area under that curve. And that is often reported in the literature as the area under the ROC curve, or AUC. So for example, a random predictor would be shown by this dotted line here, and it would have an AUC of 0.5, whereas this one that I'm showing you here would have an AUC closer, let's say, 0.7. Now, a different way of interpreting the area under the ROC curve, although I won't derive this for you here, is that it's the probability that if your algorithm if you were to take two patients, one who had a label of 1 and one who had a label of 0, and ask how of all of the patients who have a label, if you're to take two patients who have a label of 1 and a patient who has a label of 0, does your algorithm rank them correctly? Does the patient who has a label of 1, is their probability according to the output of your logistic regression higher than the probability given to you by the patient who has a label of 0? If you look at the fraction of times that the ranking is correct, that turns out to be the area under the RLC curve. And where you want to be is up here in the top left corner. So you would like to have 0 false positives and all true positives. And that would have an area under the ROC curve of 1. And now you can see that a random model has an area under the ROC curve of 0.5. Perfect model has an area under the ROC curve of 1. Now, if we think about the actual application that we set out to try to solve, we're not going to have resources to reach out to 100,000, we may not have resources to reach out to 5 million individuals because there might not be budget for that. Instead, we might only have resources to do this intensive reach out to, let's say, 2 million or 1 million individuals. And so we don't really care so much about this right-hand side of the curve. We care about what's going on over here on this side of the curve. And there's a different statistic which is often used to try to characterize that, and it's known as the positive predictive value. So the positive predictive value is a measure of if you were to take your sorted ranking. So we're now going to take the model that was trained. We're going to apply it to patient data from December 2020. And we're going to get a ranked list of individuals who, if hospitalized, who is most likely to have poor outcomes. And then we're going to say, okay, we have money to perform outreach to a certain number of these individuals to try to help them get vaccinated. For example, we might have enough, we might be able to reach out to 100 individuals. We might be able to reach out to 1,000 individuals. We might be able to reach out to 10,000 individuals. And so what's relevant is, of those 100 individuals, 1,000 individuals, or 10,000 individuals, what fraction of them actually went on to have poor outcomes if they were hospitalized with COVID-19? And that's what the positive predictive value measures. It's the fraction of individuals of a predicted set that actually have the 1 label versus 0 label. And you want that number, of course, to be as high as possible. When you then go to a decision maker, for example, you might go to Congress and ask for more budget. You might describe your approach for how for sort of your return on investment in some sense of how many more people you will be able to reach out to if you were given this much more budget. Now, I've given you a very hypothetical example, and as I'm sure you have been thinking through, there are a number of subtleties to how one would try to use this machine learning approach. And the real world really is messy and imperfect. So for example, I'd like to hear from you your thoughts. Will a model trained using data from July be useful in December? Has anything changed? So if you could take out your chat and send me a private message, I'd like to see your thoughts about whether there are any concerns with using a model which is trained using data from March to July to learn who is likely to have poor outcomes from a COVID-19 infection, hospitalization, and then taking that model and deploying it now in December or January using data up until now. Where might using that approach go wrong? I'd like to hear some responses. You can send me private chats to, and I'll just wait a moment to reach through. I'm getting a couple, but I'll wait for a few more responses. I'm getting some really interesting responses. I'll wait one more minute to see what else we get. All right, so some of the responses we heard from our fellow students are that, well, first of all, the state of the world might be different for a number of reasons. If you apply the model in December, for example, it's now winter time, and so both the data might look different. For example, patients' visits to doctors might be different in the winter time versus in the summer. Also, very importantly, the COVID-19 strain might have changed from July to December. There may have been mutations. And so as a result of that, perhaps a different set of people might be at highest risk of having poor outcomes. Another very important problem is that there may have been new treatments as well that have been discovered from July to December, and so that might also have affected who is likely to have poor outcomes. So I'll just mention a couple of these here, but you mentioned many others, and these are all really good points. And so these are things that we're going to have to take into account when we want to use such an algorithm. So, for example, you might think that the data looks very different because of some of the, let's say, weather changes. So we might say, okay, well, one way to try to address that problem is to only use data up until, let's say, March 2019. So we're going to take only the patient's data up until March 2019 to make the prediction, even if that prediction we're making in January, February of 2021. I meant to say up to 2020 instead of 2019. And so there you might be using less information. You might be missing out on some of the most recent data from patients. But the upside of that is that you have a consistent set of features that don't change much as we go into the future. Now, the second problem that you mentioned is that there are, let's say, new treatments. And that is, of course, also a big problem. And so one thing that one can do is one could take the model that was trained using data up until July, and you could evaluate how is it doing at various points in the future. For example, you could look at what is the area under the ROC curve when you take that model, that same model, and you apply it to patients in August, September, October, November, December. And you can look to see, well, despite the fact that treatments are changing across time, is the relative ranking among patients still relatively consistent? So if the area under the ROC curve is relatively the same across time, it might be that some patients' risks go down. It could be that the overall probability of everyone is shifted down a little bit due to the new treatments. But so long as the relative risk across patients is the same, then the model might still be useful. But that's an example of a sanity check that one might want to do. And of course, introspection into the model can also help with that. Okay, so that's all I want to say about that example. And now I want to move on to thinking about clustering, and a use of unsupervised learning for healthcare. So recall back to lecture 13, last lecture, where Tamara presented the k-means algorithm. She gave this example where there are two features, x1 and x2, longitude and latitude. There are a number of data points and little n data points, and critically in the k-means algorithm, there are no labels. Our goal is to discover some structure in the data. The first step of the k-means algorithm was to initialize some means. Here we chose 1, 2, 3, 4, 5 different means. So there will be 5 clusters we get out. Then the second step of the k-means algorithm assigned every data point to their closest mean. And so that's what you're seeing here by the colors. We're then going to average the data points assigned to each mean in order to get a new mean for that cluster. And then we're going to repeat this procedure over and over again until it converges and you get a final clustering algorithm out. So what I'm going to present next is an application of the k-means algorithm to solve a problem that had been presented to me actually originally a few years ago by a pharmaceutical company that was really interested in studying asthma. And this is a problem, by the way, that some of you might have noticed was the last optional question of the lab last week. So The problem is that 5 to 10% of people with severe asthma remain poorly controlled despite using the best therapy that's currently available. And so we'd like to think about can we better understand asthma, and can we think through how we could design and evaluate new treatments for asthma. In this paper published in a medical journal, The Lancet, a few years ago, called New Targets for Drug Development in Asthma, they asked the following questions. What are the processes, genetic or environmental, that underlie different subtypes of asthma? What are markers of disease progression or treatment response? And why is it that some patients are less responsive to conventional therapies than others? So we're going to try to answer these questions, or some of these questions, by using a k-means clustering algorithm on data from asthmatic patients. And the output of the algorithm is going to be a new set of clusters, which you don't have to understand this slide. We're going to dive into it in just a moment. But this is just an example, a picture from this paper published in 2008, which characterized 3 different families of new subtypes of asthma. And that's what we're going to aim to discover through this analysis. So there are going to be 3 data sets used in this analysis. All 3 are from a non-smoking population. And the first data set is of 184 patients recruited from primary care practices in the United Kingdom. The second data set is of 187 patients who were treated in an asthma clinic. So these are patients who potentially have more severe asthma because they're not being managed. Their asthma is not being managed just by their primary care doctor, but by a specialist. And then finally, we're going to have a third data set of 68 patients who had undergone a randomized controlled trial comparing 2 different treatments. And that third data set we're not going to use for a few minutes. We're going to start by using those first 2 data sets to try to do clustering to see, can we discover any interesting structure in the data, see how patients might differentiate across different asthma conditions. Here's just a very quick analysis of those 3 cohorts. So each column here is describing one of those 3 data sets. Focus on the first 2 columns. In the primary care cohort, there were 184 patients. In the secondary care cohorts, that is patients who were managed at an asthma clinic, there were 187 patients. There were a little bit more female patients in the second cohort, so 65.8% in the asthma clinic cohort. The age distributions were relatively similar, an average of 49 years old in the primary care cohort, an average of 43 years old in the secondary care cohort, and so on. And so this just gives us some intuition about sort of who are the individuals. But there's been no clustering yet. The first thing we're going to do is we're going to take the primary care cohort, these 184 patients, are going to run a k-means algorithm. I won't walk through how we choose the number of clusters, but just believe me, we're choosing 3 clusters here. So we initialize with k equals 3 means. We run the k-means algorithm, and we're now going to analyze the results. Now, the first thing we're going to do here is we're going to recognize that here we're using a relatively small feature vector. In particular, every row here corresponds to one of the features that went into the k-means algorithm. We have the gender of the individual. We have their age, the age when they had an onset of asthma, their body mass index, a measure of their lung function that's measured by this biomarker called FEV1 change, how much corticosteroids they inhaled as part of their typical therapy, how often they were admitted to a hospital or emergency room, and how many severe asthma exacerbations they had in the past 12 months. So each one of those is one of the features. And again, we're doing this clustering just in the primary care cohort. And in this first column here, I'm just giving you the average of the feature values across the whole entire cohort. Now, the way that we're going to understand or visualize the output of the clustering algorithm is by looking at the mu1, mu2, and mu3, meaning the cluster centers, cluster means of the 3 different clusters. We're also going to look at the variation or variance of each of the features among the data points assigned to that cluster. And that's going to be a number presented in the parentheses here. So we get 3 clusters out. The first cluster has 61 patients, the second cluster has 27 patients, and the third cluster has 96 patients. Let's start to try to analyze these clusters by looking at these features. The first thing that is immediately apparent is that in cluster 1, the age of onset of asthma is substantially smaller than in other clusters. In cluster 1, patients tended to develop asthma at roughly 14 years old, with a standard deviation of 15 years, compared to clusters 2 and clusters 3, where patients tend to develop asthma in their 30s. We also notice that in cluster 1, that on average, patients have had 1 previous hospital admission and almost 2 severe asthma exacerbations in the past 12 months. And that should be compared to the averages in the whole cohort shown in the first column. And so we're going to call cluster 1 the early onset cluster, patients who have early onset asthma. And these patients actually have pretty exacerbated asthma, because you can see that by their sort of not large number of hospital admissions. These names you see in the very top here are names that the analyst has given to the cluster by analyzing these means and comparing it to the overall population. Cluster 2, we see, is overwhelmingly female. So 81% of individuals in cluster 2 are female. And they also tend to have a much higher body mass index. So this is a bit more of an obese population. In cluster 3 is generally healthy. These are patients who have asthma, but if you look at their the bottom 3 features here, on average, they've basically not been to the hospital at all, and they have had very few asthma exacerbations. So these are 3 clusters that we found through k-means clustering on this one data set. And the next thing we're going to do is see how robust it is. So we're going to take the second data set of patients who went to the who were treated in the asthma care clinics, and we're going to repeat that clustering, the same clustering procedure. So initialize means randomly from scratch and rerun clustering. The set of features are very similar, but not identical to the previous data set, which is why we don't attempt to, for example, throw together all of the data and cluster them jointly. It's because we have a slightly different set of features. So we run clustering here. For this data set, the authors chose to use 4 clusters. I'm not going to comment on that, but we saw in lab and in the notes for the clustering how there are a number of different methods for trying to choose a number of clusters, such as, for example, looking at sort of kink set, looking at k-means objective as a function of cluster size increasing. So here, despite the fact that we redid the clustering from scratch, what these authors found is that very similar clusters seem to arise. So when they analyzed these 4 different clusters, they found that 3 of the clusters, cluster 1, what they're labeling as cluster 1, 2, and 3, corresponded almost identically to the clusters that were found in the previous cohort. But now there's a 4th new cluster, what they're calling inflammation predominant, which are patients who have substantially worse asthma. And that makes sense as well, because this is a slightly different population as the previous population. These patients are patients who are being managed by experts in asthma. And so there tend to be sicker patients. And so this 4th new cluster is of the sicker set of patients. Okay, so now we're starting to see something really interesting. We're seeing how these first 3 clusters were pretty robustly discovered across 2 very different data sets. Now we're going to see, so that starts to give us some confidence that there's some significance to those clusters. But now we're going to try to take that the next level and see, can we try to see if those clusters are actually meaningful in changing something about treatment, or seeing how effective different treatment might be for patients within those clusters. And that's what we're going to start to use now, the 3rd data set. Now, the 3rd data set only has 68 patients, so it's substantially smaller than the first 2. And if we were to do clustering, which we will do on these patients, we should really question the robustness of those clustering results because of the small number of patients. And that's where the alignment with the previous 2 results is going to end up being important. I'll come back to that in a moment. Now, for these 68 patients, these patients were followed over 12 months, and half of these patients received standard clinical care, but the other half of the patients received a new type of treatment, in particular, what we're going to call the sputum treatment. And this treatment strategy involves regular monitoring of the airway inflammation using the patient's phlegm and changing the amount of steroid therapy in order to try to maintain a certain level of white blood cell count from the patient's, as observed in the patient's phlegm. So that's a new treatment strategy. And the question is how well that treatment strategy works. Now, the original study, the original randomized control trial involving those 68 patients found no statistically significant difference between these two treatment strategies. Meaning, if you look at outcomes such as hospitalizations or the amount or number of exacerbations, there was not a statistically significant difference across the two different sets of patients who got one treatment versus the other. However, what you ought to wonder about is there might have been variation in the treatment response. Maybe some patients do best under that first treatment strategy, and other patients do best under that second treatment strategy. And so what we're now going to do is we're going to reanalyze these results, trying to separate out patients into patients according to those three different clusters. So the first thing that was done is taking the baseline data, so the data pre-treatment, and assigning patients to these three different clusters. And we now have a pretty rigorous definition for what these three different categories of patients should be based on the clustering done on the first two data sets. And so we're going to categorize every patient into one of these three categories, and then we're going to look at what happened according to those two different treatment strategies. So what you see here is that along the three different sets of patients, the first category of patients, what the authors called obese female cluster, if you look at the outcomes, for example, severe exacerbations and number of times that they had to start oral corticosteroids, which is a measure of severity, both of these numbers are very low. So these are patients who were not really affected by either the treatment strategy. There's no statistically significant difference. The other two clusters is where the interesting things happen. So in particular, if you look at that third outcome, you see that in the first of these clusters, the inflammation predominant cluster, in one of the treatment arms, so the regular clinical practice, you see that under the first cluster, patients do well under the typical clinical practice, but on the second cluster, they do poorly under typical clinical practice. And you see the exact opposite in terms of the patients who got the other strategy. So if you were to average these two numbers, it looks like the treatment doesn't make too much of a difference, right? If you compare 9, sort of the sum of 9 plus 0, to the sum of 2 plus 6, which is 8, 9 versus 8 doesn't look very different. On the other hand, now, if you break down the patients according to these two different categories, you see that for one of these subpopulations, it looks like this typical clinical practice does much better than sputum because we want this number to be lower. Sorry, I think it's the opposite. We want it to be higher. So the sputum category, the sputum arm does much better for this cohort. Whereas for this cohort, the typical clinical practice does much better as a treatment. And so this now suggests that maybe if one were to approve this new treatment strategy, one should approve it only for the sub-cohort of patients for whom it looks like they respond the best to that treatment. And this is just one illustration of how one can use k-means clustering to try to guide who might benefit the best from treatment. So now I'm going to move on to the second to last section of this lecture, which is about reinforcement learning of treatment policies. So think back now to lecture 9, where Tamara introduced marker precision processes, and then lecture 10, where she introduced reinforcement learning. So marker precision processes involved first, a specification of a state space. And in the simple example that she gave in lecture 9, the state space was very simple. This is a farming example, and the state space was either there's a poor soil or rich soil. And so every farm is in one of these two states. Then one has to specify a transition distribution. So according to what action is taken, there's some probability of transitioning to either or staying in the same state, which is denoted by these self loops, or transitioning to a new state. So for example, the transition distribution for the plant action, if you were to take the action of planting, then if you started out in a rich soil state, then if you were to take the plant action from the rich soil state, with probability 0.9, you're going to end up in a poor soil state. On the other hand, if you take the plant action starting in the poor soil state, there's an extremely high, so probability 0.99 now, of ending up in the poor, of staying in the poor soil state. Very unlikely that by planting you turn a poor soil into a rich soil. And one can talk about the transition distribution for different sets of actions, such as a fallow action. So that's the state space, that's the action space. We talked about the transition distribution. The transition distribution is given to you by a starting state, an action, and then asking about the probability of ending up in a new state. And so you have a probability or a real number between 0 and 1 for every cross product of starting state, action, and ending state. Now, a markov decision process also has a reward function, which tells you for every state and every state that you end up in and every action that was taken, what is the reward for ending up in that state having taken some action. So for example, in lecture, Tamara hypothesized a reward of being in a rich soil state and taking the plant action of 100, whereas the reward of being in the poor soil state and taking the action of plant was 10. She also specified a discount factor, but for healthcare settings, the discount factor, which is used to discount the effect of rewards that were long in the past, is irrelevant. In some sense, we care about the full set of rewards for patients. And so we're going to think about the reward, about the discount factor as just being 1. So I won't be talking about discount factor in any of the subsequent slides. Okay, so this is just a quick reminder of markov decision processes. Now let's think about how we might use markov decision processes in healthcare to try to provide decision support to clinicians as they manage patients who have cancer, or as they try to manage patients who have a very critical illness. And the goal of what we'll be describing is to think through how can we learn a policy pie which takes a state and proposes an action. And when we try to implement this in a healthcare setting, you think about this as taking data, learning these policies, and then using these policies to provide decision support for clinicians. So if our policy says, we think that prescribing the patient this medication, which would be an action, would result in the best future set of rewards, then one might suggest to the clinician, maybe you should be prescribing this treatment because we think the patient will respond best in the long term to this treatment. And that's an example of what a policy might be and how one would use it. So the case study that I'll be giving to you here is from that of managing what's known as septic shock. Septic shock is a condition, it's the second leading cause of death in hospitals, and it's caused by infection. And that infection, the patient's immune system attempts to fight the infection, but at the same time as the immune system being activated to fight the infection, often the immune system also ends up affecting the patient's organs that can lead to organ failure and ultimately death. And so when one wants to try to manage sepsis, of course, the first thing to do, because it's caused by an infection, is to try to prescribe an antibiotic. Then However, antibiotics alone tend to not be sufficient for managing sepsis. And there's a number of other things that one has to try to do to try to keep the patient alive once they get into this state. So for example, a patient might be put on mechanical ventilation in order to help with their breathing. Patients might need sedation because they might be very uncomfortable due to the mechanical ventilation which they were just put on. Giving them sedation might have reduced the patient's blood pressure, and as a result of that, one might have to give vasopressors, which is a machine you hook them up to in order to try to artificially increase their blood pressure, and so on. And so if one thinks about the series of actions that would need to be taken in order to optimally manage a patient with sepsis, it corresponds to a large number of actions across time. And any one patient, of course, for any one patient, you only observe one set of actions. So for this patient that I'm showing in the orange line here, they receive mechanical ventilation, let's say at time 3 hours. Then they did not receive sedation, and then at let's say 4 hours they received vasopressors and so on. And had something else happened to them, had they taken a different trajectory through this path of decisions, then they would have a different set of outcomes. But we only, of course, observe one actual patient trajectory in the data set because doctors did one series of actions to them. Had doctors done a different series of actions, then we might have gotten a different set of outcomes. And one of the challenges in trying to learn an optimal policy for managing sepsis is that there are a large number of possible actions, but only some of them are observed in the data. And I'll get back to that in just a minute. So in order to try to tackle this, the first thing that we're going to try to do is define the state space, the set of actions, and the reward function. Whereas in the earlier part of the lecture, I was giving you a hypothetical scenario around COVID-19, what I'm describing here is a paper that had been published 2 years ago in Nature Medicine. I have the reference in the very bottom here. So for the state vectors, what they did is they derived a feature vector for each point in time, which looks at both what are the most recent and past actions that were taken. So for example, past medications, looks at the patient's vital signs. For example, what is their current heart rate? What is their current blood pressure? What's their current oxygen saturation, and so on. And you get this one high dimensional feature vector describing the patient at that one point in time. Now, in order to apply the algorithms that you learned in this class, which were for discrete Markov decision processes, we want to get a finite set of states out. And so what these authors did is they took that feature vector describing the continuous valued feature of the state of the patient at every point in time. They're taking the union of all of those different feature vectors from a single patient at different points of time across patients. So now one data point might correspond to patient 3 at time step 10, for example. And we're going to do now k-means clustering of all of those different continuous valued feature vectors. And what we get out are, let's say, 500 different clusters. And we're now going to define a set of states corresponding to 500 discrete states. Every patient at their point in time is assigned a number corresponding to which cluster that data point went to in k-means clustering. And so now we have a state space of 500 different states that we'll use in defining this Markov decision process. Now, the actions were the actions that I described earlier. So for example, do you put the patient on mechanical ventilation? Yes or no? Do you give the patient fluids? If so, how amount of fluids? So you might imagine 3 different levels of fluids. And if you look at the combination of these these 2 different types of actions, that itself defines the action space. So one action corresponds to a few of these different decisions. I can't remember the exact number of actions, but let's say there are 20 or 50 different actions. Each action, again, tells you start or stop ventilation plus a level of amount of fluids to give the patient. Now, for the reward function, one wants to, of course, keep this patient healthy. And so how does one characterize healthy is one of the key design choices in setting this up. And different choices of reward functions will result in very different policies that are learned. So for example, one might just use a very simple reward function, which ignores the reward at every intermediate state and just looks at the reward at the termination states, where in this case, a termination state corresponds to either a patient dying while they're in the hospital or then being discharged and then surviving at least 30 days or dying within 30 days. Each one of those will correspond to some reward function where, of course, we're going to put a very high negative reward on the poor outcomes. Now, one might also be interested in having more intermediate rewards along the way. And this is one thing that you saw could be very helpful in learning a good policy, is sort of this type of reward shaping. And so one example of an intermediate reward might be blood pressure control. So we might know that if we keep the patient's blood pressure within some range, it's a good thing. And so if you ever see the patient's blood pressure go outside of that range, you have a negative reward associated to that. And so that's how you define the reward function. Again, the reward function is a function of the states. Here, we're going to ignore the actions when defining the rewards. So we have the states, we have the actions, we have the rewards, we have everything we need to define a markov decision process. And now the next step is, how do we learn it? So in lecture 10, Tamara spoke about exploration versus exploitation. And the key question there is you start from no data and you start exploring in the world by performing some actions, seeing what happens, what rewards you get, what states you get to. And as you do more and more exploring, you get more and more data, and you use that data to try to learn a policy that gets better and better over time. And there's this question of, do you exploit, meaning do you use the best policy that you have for all future individuals, or do you explore, meaning do you keep trying different types of treatments? And the exploration strategy that we spoke about in this class is called the epsilon greedy strategy, where with probability epsilon, you choose an action uniformly at random. Now, do you think that strategy would make sense in a healthcare setting? Any concerns with that? You can enter your response in the chat. Any concerns with using the explore and exploit strategy? So one concern is that I see people are entering is that mistakes might have a higher impact. There might be really big ethical issues with deciding who to use exploratory treatments on. And these are all really good points. And one can't use this epsilon greedy strategy in a healthcare setting. And that's what one of the major challenges is in using reinforcement learning techniques that we saw in class in a healthcare setting. I'll get back to what we do in just a second, but the TLDR of this is that there are a couple of different algorithms that we learn in lecture 10 for learning. The first approach was, let's say, just explore and then learn your transition distribution. And then once you've learned your transition distribution using all of the data you have, then you just do infinite horizon value iteration in order to learn a good policy. The second approach that was suggested was to estimate the Q function directly from the data that one has. So as we just discussed, one can't typically explore in a healthcare setting. And instead, what one does is called offline reinforcement learning. It turns out that the two algorithms I just showed you from lecture 10 could be used in an offline setting where all one has are those observed trajectories of state action reward pairs for patients in the retrospective data. So for example, you could use that retrospective data to estimate the transition distribution and then run value iteration. Or you could also just take pairs of these tuples, S, A, S prime, and R, keep presenting them to your Q learning algorithm, you're getting these pairs instead of from doing epsilon greedy, you're getting them from your observed data. And you learn, you do Q, you update your Q values based on those observed batch data. So this is what's known as off-blind reinforcement learning, and that's what we would use in this healthcare context. Now, recent reinforcement learning successes in the news, for example, the AlphaGo algorithm, which had succeeded at beating the world's best Go player, led the healthcare community to be really excited about using reinforcement learning in healthcare for problems like the one I just mentioned. But it turns out that healthcare is substantially harder than those settings I just described, those game-related settings. So for example, one key design choice is what is in that state space. I showed you one way to try to derive the state space by this k-means clustering approach based on features like the patient's blood pressure, oxygen saturation, and so on. But if we had accidentally left out important information there, then the policies that we get out could be really biased. And then similarly, we just talked about how we can't do epsilon greedy algorithms to learn here. Instead, one has to only take retrospective data that are available. And a big difference, and so thus we might have very limited data available. Whereas in these game scenario, they had simulators. So they could really think about any policy and just run that policy and see how well it does. And so those algorithms were substantially more successful as a result. Okay, so I already just gave some hints about what makes healthcare different. So I'm going to skip these last few slides, and I'm going to get to my closing slide. Congratulations. This is the end of 6036. You've had 13 lectures that walked you through everything from supervised learning to reinforcement learning to unsupervised learning with the k-means algorithm. And along the way, we've hinted at how we're really just at the tip of the iceberg. We hope that you now have some of the skills you would need to start using machine learning in an industry position, an internship, and research. But one might also want to dive in deeper to learn much more about machine learning and data science. So in terms of where to go to next, I'd like to point out a few courses that you could consider taking in subsequent semesters here at MIT. These first two courses, 6409 to 6419, are very introductory courses, but focus on more data science aspects of machine learning than what we focused on in this course. The next sort of set of four courses, 6806 up to 6802, are courses that are at a more advanced level, but many of these courses have both undergraduate and graduate versions, and they look at applications of machine learning in different scenarios. So for example, 6871 is a course I'm teaching next semester on machine learning for healthcare, which goes into much more depth on some of the things you learned in this lecture, and it requires 6036 as a prerequisite. Then there are two more courses I'd like to point out that aren't offered until the fall semester, 6867, which is the graduate machine learning course, and 6660, which is another graduate course in machine learning, which is joint between Course 6 and the Brain and Cognitive Sciences department. Both of those courses would be very appropriate courses if you want to do a much deeper dive into the algorithms that you learned about in this course and learn some of the theoretical properties. All right, with that, we're out of time, and I want to thank you for joining us for 6036 this semester and wish you a very good winter break.